today's talk will start with a quote that's actually real by this professor from Duke University. It says, you've seen it, I guess, big data is like teenage sex. Everyone talks about it, nobody really knows how to do it, but everyone thinks that everyone else is doing it, so everyone claims they're doing it. And it's kind of true. I mean, I've seen it a couple of years ago at a conference in New York, which was very different in terms of the profile of people who came to the conference. And what I saw there were people who were talking to each other, and they were saying things like, do you have big data? I've got big data. Like it's some sort of a physical, tangible thing that you have, that you own, like a product or something you license, which I thought was funny, but of course I kept it to myself. Today, I'll talk about sort of a real life big data situation that we have with our SPM product, which is a performance monitoring service and a product. And with our I'll share information about what we've done with Solr in that context, how we have experimented with it as a data store and data retrieval for aggregation, also aggregated metrics, performance metrics. For those who don't know me, my name is Otis, and I'm a Apache guy, no longer super active. But once upon a time, I was active in projects like Lucene, Solr, and Nudge. But I've been keeping busy with Sematext, the company, again, some of you know, that provides services around Solr, Elasticsearch, things like consulting or production support, as well as several products around search and related areas. One of my addictions are needles, and this addiction I realized I had in mid-90s when I went to college, when the web was pretty young, and the search engines like InfoSeek and WebCrawler, for those of you who remember, were the big cool thing. And it fascinated me that they could process these large volumes of data, index it in some way that allowed me to find something useful in the data. So back then I developed this addiction that I still have today for search. The other addiction I had was eating watermelons, slicing bread, and slicing data. Large volumes of data. For some reason that I can't really explain, maybe psychologists would be able to explain why is it that I like analyzing large volumes of data. Size matters for me here, and being able to find nuggets of information in form of reports, trends, charts, it's just something that turns me on. And in order to be able to slice and dice lots of data, in order to be able to search it, you need to, of course, first gather it. So back in college again, I remember writing crawlers that would just do meaningless stuff, really, looking back. But I was fascinated by seeing them do their work, crawl, extract links, fetch pages, and then eventually die, running out of memory because I had didn't have the skills to write this data on disk and scale it really properly. This was a while back when I was a kid. Looking back, I see that these sort of three addictions have been sort of implemented in the form of various products that have to do with all of these factors: gathering of large volumes of data, some sort of slicing and dicing, some sort of reporting, and searching. So those are sort of on the side, sort of the three criteria that match my addiction. And the first thing that we did that has to do with aggregation and gathering of large volume of data was this search analytics, which you can think of as Google Analytics, but for search specifically, with the reports that tell you about how people are using your search application, whether they're clicking on something or not, and basically providing you a good tool that serves as a feedback for improving things like relevance. So once we built this, we built an aggregation framework underneath, and we said, you know what, we do a lot of work with customers. They need help with performance, and Solr customers back then. And let's build a tool that does performance monitoring, because we could use it in our own work. So out of this search analytics came SPM, which some of you may be using or know about. which uses the same underlying aggregation framework, but the input data is different. It's not clickstream, it's not search queries like in the search analytics case, but large volumes of numbers and other bits of information. And it's going to be in this context that I'll talk about Solr being used for aggregations. And the last thing that we built here is actually not Solr specific, and it's slightly different, but it's useful for, again, matches my addiction criteria, and it's useful for those who are using Solr, because it's a tool that allows you to index your logs and troubleshoot when there are issues around performance and things like that. So going back to SPM, where we experimented with Solr, this is what it looks like on the surface. This is an example report that you see in SPM. This one specifically shows JVM memory pools, their sizes, which is helpful when you're dealing with memory issues. This is not Solr specific. You could monitor really any JVM application. And what's important here are, they're kind of fuzzy, but on the right are filters that you can use to slice and dice your metrics. So on top are actually hosts, and followed by JVM names and memory pool names in this case. For other reports, obviously there are different dimensions, and they're dynamically sort of figured out based on the data that's coming in and being processed. And things that matter for the rest of the talk here are these filters, and let's see that, which is the granularity selector that says it's a pull-down menu that actually has 1 minute, 5 minutes, and other granularities that represent the granularity at which you want to see a metric on a graph, a value of a metric on a graph. So even if, for instance, we collect data 10 times a minute, if we aggregate it down to in a 1 minute bucket, you'll see one data point. And that matters for how we use Solr, which I'll show in the next slide. Next slides. This is what's under the hood. And you can ignore the black lines and arrows, those don't really matter. This is from a diagram that we have in the documentation for SPM, the on-premise version of SPM. So I just took the diagram because we can use most of it here. On the left side is basically the server that's being monitored. And the important bits there are to see that there's an orange component over there, this one, called SPM monitor, which is responsible for gathering statistics about application being monitored. So that could be Solr or Elasticsearch or Hadoop or anything like that. This component just grabs statistics and logs it somewhere. And then the orange box at the bottom, the SPM sender, takes these logs with metrics and sends it to us over the network in batches. And when I say logs with metrics, you can just imagine it as log lines that contain things like metric values, metric type, timestamp, and other attributes, other dimensions that we can later use for filtering, like a host name. So that's sent over to us, and we receive it, and we stuff it in Kafka. And from Kafka, we consume it with various applications, various components. The top one here is Alerts Engine. I'm going to skip it. And the bottom one is the one that we'll talk about more, the AF server. AF stands for Aggregation Framework, or we call it AFS for short. And it was modeled somewhat after Solr, in a sense that this AF that sits in the core is really a generic data aggregation library that we use for that search analytics that I mentioned service and SPM. So it's generic in what it can aggregate. And the AFS is a shell around it. So it's like Lucene, being a text indexing or data indexing and searching library, and AFS is a shell around it with some HTTP APIs, just like Solr has handlers. At the bottom you see HBase, and this is where we store currently all the metric values, all the metrics, everything that gets displayed. And on the bottom right is reports web application, which is responsible for retrieving the data from this AFS. So it makes a call from here via AJAX, via HTTP to AFS, and then AFS retrieves it from the data store and returns it, I believe, as JSON, and it gets displayed in the UI. So if you look at this picture, there is no Solr anywhere, and we actually do run this in production, and it works well. It processes large volumes of data. So the question is, I think there are two questions here that one could ask. One is, where does the Solr fit in, and why? Why would we change something that seems to work well for us? So the reason why we even looked at Solr in this context is because we thought, okay, one is sort of more businessy, some are more technical. One of them we thought we want to package this for people to run on premises. So if they have Solr instead of HBase, that will be nicer for them because Solr is easier to operate, easier to manage. There's just one process, ignoring the Zookeeper for now, as opposed to HBase, which consists of different processes, region servers, master servers, and that depends on Hadoop, which has its own set of processes. In the end, we said we were able to package everything nicely without changing HBase and replacing it with Solr. But the more technical reason why we looked at it is that we thought maybe some of the Solr functionality, its ability to group data, to facet, to sort, maybe some of that, or apply function queries on results, maybe we can use it and maybe give us some flexibility that HBase doesn't give us. Two sentences about HBase. It's a distributed data store, which at some level is very similar to SolrCloud in the sense that it shards the data, that it has this region files, just like Lucene has segments and things like that. It's somewhat similar. But the only way to retrieve data from it is by saying, here's the key, give me one row for that key. Or here are the two keys, beginning and end key, scan the data and retrieve everything. And it doesn't allow you to facet or filter in any more flexible way that we thought maybe Solr could do for us in this context. So that's why we looked at Solr. So this is where it fits. The orange, sorry, not orange, yellow cylinders here. That's basically the data store where we put Solr. And luckily, this AFS is written in such a way that this data store is pluggable. So we could replace this with Elasticsearch, tomorrow, or with Cassandra, or even something like MySQL if you really wanted to. There's only a thin layer here that's not shown. That's sort of the adapter that knows how to serialize, to write data to a specific data store. And this is basically the same picture, but with all the noise stripped and just the important bits left for us. So we'll talk about this AFS a little bit, because this is our sort of aggregation engine that takes data from Kafka and reads a configuration file that consists of a bunch of these definitions that we call aggregation plan. And these definitions, which are agnostic to what data store we use, basically tell AFS how to aggregate the data so that it can be retrieved later on efficiently for displaying in UI. So here, this example is for taking the metrics that we get from Solr about its caches, and we construct a document essentially that has whose key sort of consists of a system ID, of a granularity, the name of the Solr cache, because there are several, the host name, and the core that's associated with this cache. And basically, another important thing to mention is that AFS, when it reads data from Kafka and looks at these plans and computes aggregations, it does that all in memory. So it tries to compress and combine these cubes into the ideal representation, but periodically it says, okay, I'm full, memory full, I need to flush out the data. And at that point in time, it saves data somewhere, and that's where that adapter that I mentioned that lives somewhere here gets involved, and that's where this Solr-specific adapter says, okay, now I need to actually index the data. So flushing is the term that we use, but it's really, in case of Solr, it's I need to index data into Solr. So indexing is not happening at all times. And when we do that, we typically have a ton of these in-memory documents that we need to write out. I'll talk about now how we do it in a way that is fast. Before that, I'll show the schema that we used. This is not necessarily the most optimal thing to do. This is, like I said, an experiment that we did with Solr, and this is the schema that kind of matched what we had in HBase, but adapted to Solr context a little bit. So I'll just mention a couple of these, explain a couple of these fields. The base row key, you can think of it as a field that contains something like a concatenation of these dimensions, something that identifies a data for a data point that ends up being on a graph in the end. The metrics data is the actual value of the metric, and then these two dynamic fields we use to extract host or core name or cache name, so that we can later on filter by those fields for reporting purposes. And those with sharp eyes will notice that there is, we're using doc values, and I'll talk about what we've observed there. So this is obviously when you have run a service that's not for monitoring your own metrics only, and even if it's only for your own metrics, you may have a large cluster or a large number of machines that you monitor. You need to suck in a lot of data and write really fast. So in order to write data really fast, we don't aggregate it at index time, at write time. What we do instead is we append, and I'll explain what that means really. These two blocks, 1 and 2, are blocks that represent documents that are flushed out at 2 different times, TS1 and TS2. You can see it here and here. So if you imagine that this AFS component that we have can hold only a little bit of data in memory and has to flush, meaning index data, twice a minute, then even if we get 10 measurements for a certain data point, like a disk I/O for the same host for the same time bucket, if we get it 10 times in a minute, let's say, we'll still have to write out the same. We'll have to write out data for the same data point multiple times in a single minute. So that's why you'll see here 1201, 1201, same application, same host, same metric, but 2 different times. So what that, and different values because the measurements were different. So what that means that for the single data point that's in the graph, we actually have 2 pieces of data, 2 documents in the index. And the idea is that this is faster than aggregating at write time, because at write time what we would have to do is say, here are some new measurements, like values for disk I/O 70. We would have to say, what is the old measurement for this same metric for the same bucket, same host? Let's retrieve it from the index. Let's merge it with this new value and write it back into the index, which would be slow, especially because there's a delete and add at Lucene level for documents that you probably know. So the hope is that we'll just write it quickly now, and we'll compact it at some point later in time, so that in the end we end up with just a minimal number of documents. So this one representing a single document for that has all the data for this particular time range, this host and this metric. And in our SPM, we actually do end up with something like this, thanks to this project, open source project that we've created, which does this compaction for us in HBase world, but we don't have such a thing for Solr. And this HBase HUT basically allows us to append to HBase by overwriting what put in HBase does, which normally we just overwrite a row with a certain key, but in this case, when we use it, it sort of acts as a facade, so it doesn't actually put a row, it doesn't replace a row, it appends. And then...
I'm sorry, I'm just having a little trouble following. Can you just explain where you doing this in fashion because you're logging things at a finer level of granularity that you really ultimately?
Sort of. So let's say if you imagine that slide where I said there's SPM monitor and SPM sender. Imagine that that thing takes measurements, every 10 seconds, and let's say it sends it to us 6 times in a minute. We'll receive 6 data points, and in memory we will aggregate it in that AFS. We will create this cube, and it's going to be a single piece of data. But then when we flush it out to disk, if we have to flush frequently, let's say twice a minute, then we'll flush it once at, I don't know, 12:00, and flush it again at 12:00 and 0 seconds, and 12:00 and 30 seconds, maybe because that's the flush frequency that we have to have, and we're going to end up with 2 documents. It's for the same bucket, for the same time period, for the same metric, but we end up having 2. We wrote it twice, 2 different values, so they end up being 2 different documents. And that's why we end up with sort of taller index than we ideally would have. Ideally, we would have this, right? But in interest of speed, of writing speed, we just dump it in. That's faster. And you want this ideally because fewer documents means you're going to retrieve the data faster. And we were hoping that Solr could actually help us with this, that it could do some collapsing or grouping or something like that, and it turns out that it couldn't do this quite for us today yet, but it will soon. So what we do is, instead of compacting like that, we just leave these documents like that, multiple documents, and what we do is we merge them on read. We read all of these documents from the index for a certain if you're a user and you say, show me data for host 1 for this IO, and you select the time frame that includes this time range, then it will this AFS will retrieve this document, and it will also retrieve this document because it's the data that you need. So it will merge it on the fly, kind of like this. Basically, I just shrank the rows here, right? So it will merge it somewhere here, and the call or the web application that needs it for the graphs will just get a single data point here and a single data point here. But like I said, we're hoping that Solr could do this for us as opposed to us having to do it manually. The reason why we do it manually is because we just can't rely on Solr really, but ideally it would do it for us. The reason why it would be nice if Solr did it for us, because one of the reasons is because it could do it in a distributed fashion, potentially on multiple servers, as opposed to us doing this merge, on a fewer number of these AFS instances. This is what our queries look like. They're pretty simple. The important bits are that we use routing. We use this seems to be dimension for time range. This, I don't know what it is. It's encoded, but this may represent a host name. So maybe we are filtering for a certain host name and for something else. And the thing that jumps out is maybe this large number of rows, which is a no-no in Solr world. You don't want to do that. So the reason we have this high number, it's a slightly arbitrary high number in a sense that we know that number of rows that we may retrieve may be high because there are these multiple rows, and we don't want to be in a situation where we retrieve partial data, so we have high number. But we actually haven't seen that exceeded. This is an experiment, so we would not if we saw this with our client, if our customer were doing this, we would say, we need to go and fix that. That's not going. And we actually see it. We just saw it yesterday with some client. But this is an experiment, so this is what we kind of used. If we really went to production with this, we would obviously want to change this by reducing this number of documents in one way or the other. Because this is a write-intensive application, we pay attention to any kind of improvements in Solr that can help with writes. So these are a couple that live in Solr 4.5. If you need a reason to upgrade, those are good reasons. These issues. Specifically this one here, and I'll show in the next slide the comparison of Solr 4.4 without this functionality and Solr 4.5, which has this functionality, and the difference it makes in terms of performance. the last issue there is made up. It doesn't actually exist. It's just something that occurred to me, that this compaction, if we wanted to do it, we could do it through a custom update request processor that retrieves the old data, merges it, and writes it without having documents travel over the network. So this is our comparison of 4.4 and 4.5. I didn't include any graphs here to prove that the performance is better, but I can tell you that we saw faster AFS flushes, so faster indexing. We have ability to graph custom metrics in SPM. So this is how we actually measure this. We basically timed how long it takes us to index. On the graphs, we saw that with 4.5 we were able to index more documents in the same period of time, and for some reason we had lower heap, although I don't know why that is. That we didn't look into. So 4.5 is definitely better. So this cloud Solr server, if you don't know, is basically this Solr server that a piece that knows where to send the data. It knows where in a SolrCloud cluster leaders are, and it sends documents straight to them, as opposed to relying on Solr taking care of that. Normally, you can send your data to any node in Solr, and Solr will say, "Okay, this needs to go there," and it will send a document there, and it's great because you don't have to know much about the cluster. But it's a network hop, and when you write a lot, that matters. So with Cloud Solr server, that network hop doesn't happen. The data goes straight to where it needs to go. Doc values we used again to see whether they would help us in our context, and you see them in red. We have it on a couple of fields, and doc values are a feature that have been in Solr since 4.2 version, but I feel like they haven't been really well, first of all, they haven't been documented a lot. These links at the bottom that you see are really probably the only two places that have some meaningful information about doc values. And they haven't been sort of popularized. I haven't seen them much in our clients' installations. I haven't heard people talking about them too much. Some people are looking at them when they run into issues around things like faceting, because these doc values are basically kind of the opposite of the inverted index in terms of the data structure that allows that is more suited for things like grouping, faceting, and sorting than existing implementations like field cache at Lucene level and Solr. So the doc values are data structures that are built at index time. You actually see them as files in the index directory. And they're compressed nicely, and they can be read off heap as opposed to in JVM heap, which is nice for garbage collection. It puts less pressure on garbage collection, and they can be read only partially in memory and be kept on disk as well to keep them small. And we'll see actually that actually has an impact. So we made a measurement of doc values. And no doc values, and we basically saw that we end up with noticeably smaller heap. We observed more numerous but shorter garbage collections. We didn't see any change in query latency, but I think we would, and we didn't see it because we don't use facet. If you remember the query, there was no faceting, there was no sorting, there was no grouping. But if we were to use it, doc values, I think, would help us. And that's kind of where we started. We thought for analytics, we could use Solr, and we could use some of this functionality in Solr, faceting, grouping. But it turns out we couldn't quite do it because this distributed support for some of this functionality is not quite there. And we need distributed support for those features. And we didn't see any slowdown in indexing, which is slightly suspicious because there is more data being written to disk. But our tests were not super scientific either. So here's just a graph that shows that here is actually, it says 600 million, and here it says 400. So you can see that the heap is around 300 here and around almost 600 here. So it's quite different. This is with doc values, and this is without doc values. So if you have large indices, if you facet on them, or sort on them. Doc values can help because they're more efficient than field cache is, which is typically used for sorting and faceting.
Is it possible to just somewhere else than the file system cache?
Well, it's possible. I mean, in this case, this has nothing to do with the file system cache. This is the heap size. This heap size. So there actually was a graph that I didn't want to include to avoid this sort of kind of question, because you could see, there was, when we used doc values, that all of a sudden you saw more free memory in terms of how the OS sees memory. And I thought to myself, why would there be more free memory in this case? And I'm guessing it's because simply when we measured things, the OS didn't have time to cache something else. Because if it had time, it would make use of all of that memory. But we called it at a time when it didn't cache anything yet, and because some room was made in the OS cache because suddenly we were using less JVM heap, there was this gap of free memory, right? But it would get filled up soon with something else, right? But this matters to us more when it comes to garbage collection, when it comes to heap size, out of memory errors, and so on. So doc values are useful for that. And I spoke to somebody yesterday. That person is not here. Who was asking how to make their faceting faster. It's very slow on a large field that has a lot of tokens, and the answer is consider using doc values. They're more suitable than the underlying data structure used for faceting if you don't use doc values. Finally, these are sort of features that are missing from Solr for analytics, for aggregations. And all of these features, except for the Lucene one, which is committed, all of the other ones are not committed. They have patches. The work has been done, but they're just not committed. So the first one, Lucene one, we thought we would use maybe in that custom aggregating update request processor, where we would say, oh, let's retrieve all data from the index, let's merge it, but let's only change the numerical part, the metric value, and then persist it. So that would be more efficient than reading, merging, deleting the old index and putting, deleting a document and putting a new one. But there is actually no Solr integration yet. It's at the Lucene level. The other issues have been around for a while. You can see the number, but I think they're just kind of big, and nobody dares to commit them. Nobody has strong enough itch. A couple of other ones like these ones here would allow us to avoid having to do merge on read in that AFS component. We could collapse things and aggregate them when we retrieve them and have them aggregated by Solr. But like I said, this is not in yet. The important part here, from my point of view, is that Solr is a good tool for things beyond search, for analytics, for analytical queries. And to make it even better, things like this need to be in. For those of you who are keeping an eye on Elasticsearch or using it or evaluating it, the Elasticsearch team, development team, is working on basically same sort of stuff. If you pay attention to the messaging, to where the effort goes, there's a lot of effort, a big emphasis on this, not only on search, which is because these Solr and Elasticsearch projects essentially are very good distributed databases, kind of NoSQL databases that have the advantage over things like HBase or Cassandra that have this built-in search functionality, whereas in NoSQL world you have people struggling with secondary indices. How do you retrieve data on something other than the key? In Solr world that's a given, right? You just search by a field that's indexed, right? So they try to tackle this by adding another index or adding some support for secondary indexing to this NoSQL solutions. But in Elasticsearch and Solr, you see developers working on this sort of stuff, which will make these tools great analytical solutions. And that's all I've got, I think. Yes. Oh, coupon if you want 20% off for SPM. All right. Thank you very much.